Okay, in video 2, we are going to again find the center of mass by integration. This is part 2, and it goes with the second example. I hope you've tried this already and done your best. Perhaps you've actually gotten the right answer. We'll find out. In this particular example, the density of the rod is actually going to be getting higher and higher. So if you think about the rod, it's kind of like it starts off with a density of 0, and then as you go on, it's going to get denser and denser and denser. So by the time you get out to this end, it's going to be very dense. And it's going to do it in a very steady sort of a way. Okay? So this is kind of weird in a way because meter sticks are not like this. A meter stick is uniformly dense. So we have to imagine something where the density just keeps getting denser and denser. Probably a more realistic thing to imagine for this would be if you had a right triangle, like a cutout from a sign. That's sort of, a right triangle does this sort of thing. If you look at the mass contained in the right triangle along the x direction, the mass is going to grow. Because when you're close to the origin, the mass is very small. And then as you get further and further out, right, these chunks that you take are going to get kind of bigger and bigger as you go. And so I hope you can see from the geometry of this that these chunks are their height's going to increase in a linear way. So, this example that we're going to do, it could be a rod of increasing density. It could also be finding the center of mass of a right triangle along the x direction. They're really kind of the equivalent problems. So in a problem like this, if the density is increasing linearly, what you're going to want to do is basically to make a statement like this, that your lambda here is going to be equal to alpha times x. There's going to be a direct proportion. So again, the lambda here is going to be something like in grams per centimeter, right? It's going to be a linear density, and that density is actually going to be dependent on x, so that when x is equal to 0, the lambda is equal to 0, right? That's when you're over here at the tip of the triangle. But then when x is something that's big, then lambda is going to be at its biggest value. Okay, so x is changing because that's going along here. This is your x. And this alpha is going to be kind of your proportionality constant. Okay, and I'll kind of leave it to you to think about what units alpha should have in order for this to work, right? Because if I take alpha and I multiply it by meters, I should be left with grams per centimeter. So I'll kind of leave that as an exercise for you to figure that out. All right, so if this is our situation. The density is increasing in this particular sort of a way, and we would then expect that since lambda is equal to m over length, that dm over dx should also be equal to lambda, right? Because whatever's happening along this thing is going to be happening at every specific place. So I'm going to replace lambda with dm dx, like we did before, and then I'm going to set that equal to alpha times x. Okay, and then again we do the same game. We're going to rearrange, and so my dm is equal to alpha times x times dx. So I'm doing the exact same thing I did in the first problem. What I'm doing is I'm thinking carefully about writing down my density in terms of these differential terms, dm and dx. Okay, and then I'm going to rearrange that so that I've got dm by itself, and because that's the thing I want to kick out when I do the integration. So again, we're going to divide the page into two sides, and we're going to evaluate x dm first, and then you're going to evaluate dm all by itself. And down at the bottom, we're going to divide numerator by denominator, and that's going to tell us where our position is. Before I jump into this, maybe it's kind of instructive to think about where would you predict it to be, right? So if this is your rod of length L, would you expect the center of mass to be right in the center, if the density is increasing? And I'm kind of hoping that you don't. Okay. If you look at the triangle, maybe it's a little more obvious that we would kind of expect the center of mass to be closer to the right end of that object, just like we would expect it to be here. So when we get an answer for this, when we divide this integral by that integral, and we solve for x, I hope it's going to be something that's bigger than L over 2. All right, so let's do the integration here. So x dm, it's going to become the integral of x, which I'm copying down, and then I'm going to fill in the rest of the stuff, alpha x dx. Again, the reason for doing that is we can go from 0 to L. Let's do this one quickly. Alpha comes out, and then you've got the integral of x squared dx. Integral of x squared is going to be 1/3 x cubed. This is alpha over 3 x cubed from 0 to L. People who are in Calc AB, I highly recommend that you write these steps. Okay, don't skip any. And then when you evaluate that, that becomes alpha L cubed over 3. All right, let's go over to the other side. We're going to have here the integral of alpha x dx from 0 to L. And alpha comes out. Integral of x dx from 0 to L. That becomes alpha times x squared over 2 from 0 to L. And that, of course, is just alpha L squared over 2. Okay, so this top part reduces to that. The denominator reduces to that. So our center of mass is going to be, again, I'll write this out, x dm over dm, right? That's our definition. But we've done all the hard work now, and we know that that top part is going to be alpha L cubed over 3. We know the bottom part is going to be alpha L squared over 2. And of course the alphas disappear, so it really doesn't matter what the proportionality constant is, what value it has. My L cubed, the cube gets canceled by that. And I've got 1/3, what is this? 1/3 L divided by 1/2. No L's right there. And of course, kind of flipping things around, that's 2/3 L. So the center of mass that we're figuring out will be 2/3 along the length of the rod. Starting off, at 0, it's going to be someplace out here. So center of mass, 2/3 L would be right there. And that's pretty much where we predicted that it would be. And that should make sense. So same thing for the right triangle. Is if you go 2/3 from the corner, that's going to take you to the center of mass right here. Okay. What's also kind of interesting is let's say that you've got this right triangle, and you know that if you go 2/3 the distance there, that's going to put your center of mass, say, right about there. Also, if you were to go 2/3 of this dimension, whatever that height is, right, 2/3 of that height, from this corner, that takes you to a center of mass position here. And the idea is that kind of locks you into the overall center of mass for the shape. So if you want to find the center of mass of a right triangle, you go 2/3 in from either corner towards the right angle, and you find out where those lines intersect, and you should be able to balance the right triangle at that point. That would be a neat little thing you can do. Cut that out from a piece of cardboard and try it out. Okay. All right, so that's the second example. There's one more example you guys are going to try, part 3, and that one is very similar to this, except we're going to add kind of a constant term to this. So it's going to be sort of a trapezoid that you're going to solve. Okay. And we'll let you guys get a start with that. So good luck. and then you can check part 3 to see if you did it right.